Hello, everyone. My name is Andrew Nathan Kristianto. I'm a mechanical engineering undergraduate at Bandung Institute of Technology. Today, I'm going to share with you a project of mine that I've done. It is about a transient lumped mass heat transfer of a ST37 cylindrical mass. Okay, so to start off with, let's explore what the phenomenon that's been observed in this experiment. So basically, the purpose of this experiment is to demonstrate the unsteady, the transient heat transfer to a lumped mass utilizing a simple geometries. So in this experiment, we are using a cylindrical dimension. So where the lumped mass capacitance means that the temperature gradients within the solid may be neglected. A comparatively simple approach termed the lumped mass capacitance. So basically, the lumped mass capacitance is a method for conduction analysis developed under the assumptions that within the solid, for both cooling and heating processes, the temperature distribution is uniform. So from Fourier's law of thermoconductivity, a uniform spatial temperature gradient is not possible. It's not real for a real system. So if the internal conduction resistance of the solid is very small compared to the convection and radiation resistances at the surface, the lumped capacitance method provides a reasonable approximation for the temperature throughout the solid at any given time. The Biot number, in this case, is 0.159. A dimensionless ratio of the conduction resistance of the convection and radiation resistances at the surface is used to check the validity of the lumped capacitance method. So if the Biot number goes above 0.1, then the lumped capacitance method is not applicable for that case. But if it is under 0.1, then it is reasonable to use it. Next is the equations that are used. Three simple equations: the Biot number and the temperature distribution against the time constant. And to find the heat transfer coefficient, we use the third and final equation. Next is the experiment objective. So by the end of the experiment, a value of both time constant and heat transfer coefficient is found, determined for the cylindrical ST37. Knowledge of the time constant enables an analytical curve of mass temperature versus time to be drawn and compared to measure temperature response. So after doing the experiments, after we jot down the datas from the experiment, a slight curve can be drawn where the temperature against time will illustrate the temperature increasing or decreasing for both heating and cooling processes. The apparatus that are needed for the experiment are two thermocouples. One is for measuring the temperature of the fluid, and one inside the cylinder. The two is one ST37 cylinder with a drilled hole in the middle. So the drilled hole purpose is to actually plug in the thermocouple probe inside to measure the internal temperature of the cylinder. Third is a timer to measure, to again jot down time. Boiled water, a bowl, and a boiling pan so you can heat up the water. Ice water, tongs. The tongs are a really crucial, apparatus in this, because where after you actually are finished with the heating process, you need to immediately and safely transfer the cylinder from the hot water to the cold water. And then pen and paper to jot down the timer. Okay, so moving on, this is the experiment procedure. So first, we prepare all the apparatus in a spacious and flat table where nothing is harmful. And then calibrate each thermocouple with cold water or room temperature water just to check if the thermocouple is doing perfectly fine. So basically, calibration is to minimize any measurement uncertainty. And then, before anything else, we prepare ice-cool water in a bowl so that before transferring it to the ice-cool water, it's all prepared. It's just a matter of transferring it safely. So yeah, keep that on the side, the ice cold water. Once that's done, prepare the boiling pan on top of the stove and fill it up with water into a boiling pan with a thermocouple measuring the temperature. After it reaches a certain temperature, in this case it's 90 degrees ish for the boiling water, immerse the mass inside the boiling water. Once the mass is inside the boiling water, simply plug in the thermocouple inside the cylinder to measure the temperature. So after that, you every 10 seconds, jot down the temperature inside the cylinder with the pen and paper. Before actually transferring the mass to the cold water, you need to check if the temperature inside the cylinder is stabilized for a certain amount of time. So before it's being stabilized, you can't actually put it out to the cold water. So once it's stabilized, carefully using the tongs, transfer the mass and thermocouples simultaneously into the cool water. And then do the same thing again. Every 10 seconds, you jot down the temperature inside the cylinder. Once that's stabilized inside the cool water, you can pull it out and the experiment is finished. So, what data did we get from that experiment? Before anything, the dimensions of the SD37 is this: diameter of 3.5, volume of that, surface area of this, and the temperature is defined. So TO is the internal temperature of the cylinder, which I got before doing the experiment. And the T fluid of the cold water and the T fluid of the hot water is written down as that. Thermal properties of SC37 for temperatures in that interpolated is this 7880 kilograms per meter squared, and the specific heat of 472 joules kilogram per degree Celsius. Okay, from the experiment after the heating process, we jot down every 10 seconds, which represents a temperature. Simply transferring that to a graphical illustration to the right is this. So you can see over time, the temperature increases for the first 20 seconds rapidly, but then after that, it was hard for it to increase temperatures. The next is the cooling one. So this process, again, same thing, instead of heating, but it's just cooling. So as you can see, the more time we go, it's the more hard it is for the cylinder to decrease its temperature because due to the cold fluid. So the analysis, so that previously shown, the data above, consisted of both cooling and heating processes. However, there are significant differences between the time constant and heat transfer coefficient for both heating and cooling processes. However, let's just start with how we got the answers. So from using the second equation previously shown, we can find the time constant. So the time constant for the heating process is 34.774 seconds. And as for the heat transfer coefficient, we can use the third and final equation, plugging in the time constant and everything else that we've defined earlier to find the heat transfer coefficient, which is that. And that's for the heating process. For then the cooling process, it is then taken the same, however, it is different. See, we can see that time constant is different, and also the heat transfer coefficient is different from the heating process. So, in conclusion, both values of time constant and heat transfer coefficient are obtained through this experiment. These two values have, again, significant differences in the cooling and heating process. One of the factors that may affect that differences is that in this experiment, there was about 20 seconds of transferring the mass of the hot to the cold water, having a delay of immediate cooling process. So, unfortunately, the mass fell over the table, messing all the apparatus up. So that 20 seconds of delay of rapid cooling section was supposed to happen in that little mess there. And additionally to that, the accuracy of a thermocouple is really important. In this case, the thermocouple had an uncertainty of plus minus 2 to 3 degrees Celsius. So, in conclusion, The measured and calculated curves are much more in agreement for the case of heating rather than for cooling. The magnitude of the convective heat transfer coefficient is high, which suggests very strong convection or possibly moderate boiling. Thank you for your kind attention. I hope you have a pleasant day, and goodbye.